Good evening, everyone. Welcome to the LSE. Welcome to this panel discussion on parallel universes, co-sponsored by the Forum and by the British Society for the Philosophy of Science. Parallel universes, worlds just as real as our own, inhabited by counterparts of us, living out very different lives. Common trope in sci-fi, also an idea that philosophers have talked about a great deal over the years. The background to this event is that over the past 20 years or so, physicists and philosophers working on the foundations of physics have come to take this idea of parallel universes increasingly seriously as a picture of what our world might actually be like at the most fundamental level. That these parallel universes might really exist. And broadly speaking, two camps can be identified. I mean, there are those who think that this idea at first glance is really silly. But when you look carefully at the experimental data, you start to find it more and more believable that this is actually the kind of world that quantum physics is revealing to us. And then there's a camp that thinks, well, at first glance, this idea is really silly. And, but then you look carefully at the experimental data and you find that, in fact, it is still really silly. And we've got both camps, I think, represented on tonight's panel. A prominent proponent of what's come to be known as the many worlds interpretation or Everett interpretation of quantum physics, Professor Simon Saunders from the University of Oxford. A skeptic, it's fair to say, of the many worlds interpretation, Professor Fay Dowker, Professor of Theoretical Physics at Imperial College London, and Dr. Eleanor Knox, a Senior Lecturer in Philosophy at King's College London, who will be a kind of mediator to introduce the debate to us and also to kind of keep these two away from each other if things get a bit rough later on. To give you a sense of the format for the event, first of all, Eleanor is going to say a few words to try and give us a sense of what this debate is all about and what the key issues are. Then Simon will present his case for parallel universes, for the many worlds interpretation. And then we'll have some critical remarks from Fay, who favours a somewhat different view. Then we'll have a conversation about these issues among the panel, and then you'll get your chance to put your questions to the panel towards the end. So first of all, I'd like to invite Eleanor. Eleanor, what is this debate all about?
Okay, great, thank you very much. So, parallel universes, that's what we're here to discuss. I mean, as Jonathan says, it's a truly extraordinary thesis, that there really are multiple parallel universes. That's something we should actually believe in because of our best physics. Now, it's a cool idea. Science fiction authors love it. It's useful in literary fiction. My students sometimes think it's really cool, right? But I think one thing the panel can entirely agree on is that that's not a reason to believe in parallel universes. An extraordinary thesis, like the idea that there are really literals and multiple copies of you in different universes, that kind of thesis needs absolutely extraordinary reasons to believe in it. And I'm sure Simon would agree with that. He just thinks that those reasons exist, and perhaps Fay disagrees. So what I want to do right now is just give you a flavour of what kind of theory could possibly lead us to believe in something as extraordinary as multiple parallel universes. And that theory, of course, is quantum mechanics. Now, the first thing you need to set the stage is some understanding of just how successful quantum mechanics has been as a theory. There are hundreds of electronic devices in this room that would not function were it not for the laws of quantum mechanics. Our theory of the atom, our chemistry, our nuclear physics, our particle physics, it's all based on quantum mechanics. Huge amounts of technology is all based on quantum mechanics. It is quite literally the most successful physical theory that has ever existed. So you've got to start with that. The evidence for quantum mechanics is simply overwhelming. But at the same time, quantum mechanics is a very odd theory. Again, that's something on which everyone can agree. It's a theory of our most fundamental particles. It's a theory of lots of things, but one way of describing it is a theory of the very small, a theory of how fundamental particles behave. And if you were dreaming up what a common sense theory of how fundamental particles behave might be, you might think it would do something like the following. It'd tell you about particles, it'd tell you what particles there were, it would tell you sort of where they were, how fast they were moving, their mass, their charge, maybe some other properties. It would give you a kind of laundry list of properties for each particle. And then it would give you some rules about how they all bumped into each other and interacted. That was Newton's picture, very roughly. Right? Quantum mechanics doesn't do that. It doesn't give us a list of what you might think of as determinate properties for very small things. It has this very strange feature. And the very strange feature is as follows. If it's an acceptable quantum description of a particle that it might be located over here, and if there's an acceptable quantum description of a particle such that it might be located over here, it's generically the case that there's also a possible way the particle could be, where it's in what we call a superposition, a kind of state where which looks on the face of it as if it's over here and over here. Kind of add the two original states together. And that's not always an acceptable way for quantum mechanics to describe some kind of particle. That goes for all properties. So quantum mechanics doesn't give you, on the face of it, at least if you look at the mathematics and the mathematics that we use, it doesn't give you something like a determinate set of properties for each particle. And that's very odd indeed. And you might think, well, that's too odd, right? Doesn't sound like the kind of thing that could ever give us predictions. Suppose I want to predict, we have a particle detector, and I want to predict whether I'll see a particle over here or over here. Well, a good theory is going to not tell us, I don't know what it is for a particle detector to both detect a particle over here and over here. That's a kind of nonsense, right? So then, how do we get predictions out of quantum mechanics? Turns out that when something's in one of these funny superposition states, one of these over here and over here states, turns out that what quantum mechanics tells you is there's a probability of finding the particle here, and there's a probability of finding the particle here. And at this point, you might just breathe a sigh of relief. I think, well, that's fine. We use probabilities all the time. They're not a big deal. There's nothing metaphysically mysterious about them. I tell you right now that the probability that my 2.5-year-old daughter's in the bath right now is about 50-50. I'm not telling you she's in some weird half in and half out of the bath state. Right? I'm just telling you that given what I know about my 2.5-year-old daughter, she might or might not have had a tantrum by now and refused to get into the bath. But of course, there's some matter of fact about whether she's in the bath right now. I just don't know which one it is. So I assign a probability because I'm ignorant of the state. But here's the kicker about quantum mechanics. That nice, natural way of thinking about probabilities, where when the particle is both over here, and we interpret it as a probability of finding it here and a probability of finding it here, we just think, look, the issue was we didn't know where the particle was. The particle was always somewhere. We just didn't know. We were ignorant, and the probabilities reflect our ignorance. Quantum mechanics itself, the way it produces predictions, seems to block that way of thinking about the probabilities. So this is a little experiment that Simon's going to go into in lots more detail. But all I want you to get for the time being is that in this particular experiment, what I'm going to do is I'm going to take a photon, and I'm going to fire it out of a laser. And it can be, the quantum description of it at least, or some beam of photons, if there are lots of photons, can be split in two and go along two paths. And in this particular case, this is one of these cases where the quantum state, the quantum description, is going to, in this sense I'm being a little bit vague about, describe the photon as both going along path A and going along path B. And all I need you to get for the moment is if it's in that kind of state that we describe like that, only detector 1 ever fires. But now suppose I just sent a photon along path A, and I did that a few times. I'd get firing at detector 1 and detector 2. If I just sent it along path B, I'd get firing at detector 1 and detector 2. So there is a difference in the formalism of quantum mechanics between thinking of a particle as either going along one path or along another, and thinking of it as being in one of these special superposition states. It doesn't look as if I can just think that, say, I think there's a 50-50 probability of finding up path A or path B. I can't think of that as just it's either on path A or path B all the time. This phenomenon is interference. The two bits of the quantum state interfere with each other. They mess around with each other in a way that affects our predictions. So there isn't a straightforward way. There are some very complicated ways, but there isn't a straightforward way of just thinking of those probabilities as ignorance interpretation. So there isn't a simple way to get this back into common sense. Simon's going to tell you a bit more about some ways that we might try and get this back into maybe not quite common sense. Now, what's going on here is that there are two attitudes we can take to this quantum state, these funny superposition, neither here nor there, both here and there, whatever you want to call them, states. One attitude we take before we do a measurement. We take those states seriously. We use them to predict interference effects. The other attitude we can take is immediately after measurement, where we think they just predicted probabilities. Those are two different attitudes to the same state, and they don't look very compatible. What makes the difference to when we think about one state or the other, one sort of attitude or the other? This thing called measurement. Now, this is a public talk. And you might think, well, there's loads more that physicists could say about what measurement means, right? She's just not going to go into the details. But here's the weird thing. There really isn't a lot more in the traditional, orthodox, old-fashioned quantum mechanics story to be said about under what circumstances we have these funny both here and there states and when we just see one particular measurement at a detector. The only thing that we know is that when we observe or when we measure, we see things as being in just one place. But before we do it, we have to kind of think of them as being in more than one place or in more than one state, in some sense, or in this superposition state. So that should rightly lead to the question of what on earth counts as a measurement. You'd think physicists would be all busily working away at solving the problem of what counts as a measurement. And, I mean, you'll see that there's a picture of a cat on the screen. And I think, if anyone knows anything to do with quantum mechanics, they think that it's got something to do with a cat, right? So, we had to bring in the cat. Why have I got a cat on the screen? Well, for these purposes, I just want to really, use this in much the same way that Schrödinger originally did, just to push how problematic it is that we don't know. We don't have a good definition of what counts as a measurement. So Schrödinger said the following. He said, pop a cat in a box. And pop it in a box with one of these weird quantum superposition states that's sort of neither here nor there or both. And put some measurement device in that's going to measure which one it is. And then have, if it measures, it being over here, it's going to break a vial of poison and the cat will die. And if it measures it being over here, it's not going to break the vial of poison, the cat won't die. And he says, close up the box. And at the time he was writing, people were really being serious about the fact that it was human observation that made the difference about whether these things had definite states or not. So one of the things he was pointing out is if you believe it's human observation, you're committed to the fact that you close the box and the cat itself goes into a superposition state, one of these crazy dead and alive states. Its body is down here and it's over there. If you take the attitude that you take to the quantum state before measurement to the cat, you seem to end up with something that virtually makes no sense at all. But of course, if you don't want to take that attitude to the cat, you better say what happens beforehand, at what point we think we have to go from seeing the quantum state in this neither here nor there way to seeing it in this determinate way. And that is the measurement problem. That's the great puzzle at the heart of quantum mechanics. And one sign of whether you've given an adequate interpretation of quantum mechanics is whether you've given some kind of sensible, definite answer to what happens to Schrödinger's cat. And at this point, I'm going to hand over to Simon, who is going to tell you what happens to Schrödinger's cat.
Thank you, Eleanor. That was a wonderful presentation, and I've got to live up to that. I'm going to use a lot of slides, but I want to try to convey some of the concepts, because I think without that, we're a bit lost. Okay, Hugh Everett. Died young, 52, PhD thesis, 27 years old, from one of the most eminent departments of physics in the world. John Archibald Wheeler was his supervisor, he who coined the term black holes, and in the US put gravity back into the picture of the mainstream of physics. His thesis was 9 pages long. We should all write theses like that, and I speak as someone who has to read them. I don't think any other PhD thesis in physics has ever had remotely the impact of this short piece. But alas, he paid a price. This thesis more or less ended his career. And why? What was going on? So what he put forward, now known as the Everett interpretation, also known as the many worlds theory. What I'm going to do is try to give you an idea of his main ideas in that thesis, and where we are now. One component of it, Schrödinger's cat, I want to show you why, when Schrödinger presented this, it was a bit of a joke. Now, post-Everett, and 60 years ago it was that Everett published his work, the claim is we really have to take this very seriously indeed. That's one aspect to it. Another aspect to it is why so many physicists are increasingly taking these conceptual questions in quantum mechanics seriously. I'm just giving you an example. Steve Weinberg, this is from his New York Times book review article. I'm not as sure as I once was about the future of quantum mechanics. It is a bad sign that those physicists today who are most comfortable with quantum mechanics do not agree with one another about what it all means. and the dispute is about the measurement problem. Okay, I want at the end to try to explain why we're now in a rather different situation than we've been in before, with respect both to this interpretation and quantum physics more generally. Okay, now here's the hard bit. I'm going to try to go over this in a little bit more detail than Eleanor did, to impress upon you the kind of reasoning that leads us to the view that if you were involved in a measurement like this, something very, very strange would happen to you. Okay, we're starting off with a particle, actually a photon. The idea is that this is a laser. We understand there's a half-silvered mirror, and here we have fully silvered mirrors. Half-silvered mirrors allow half the light to go through and reflect half the light. Now, the fundamental character of quantum theory that became apparent very early on, more than 100 years ago, is that if you look at radiation and you go to very weak electromagnetism, propagating radiation, you find it comes in particles, in chunks. It's more like a machine gun than a wave. But then sometimes it's more like a wave. When you detect light, and you have very feeble light, it is always a particle. You detect a localized event. So we can perform this measurement when only one particle is in the apparatus at a time. Okay, now if we do that, we have to conclude one particle at a time we build up statistics of detection events, but we have to conclude that the particle cannot be traversing path A or, exclusive or, traversing path B each time a particle goes through. And the reason we can't do that is because if it did, we'd have, say, this situation on one occasion, but then the detector D2 would fire with 50% probability. And it can't have taken the other arm either of the this is called an interferometer, because the detector D2 would have fired with 50% probability. Instead, we find D2 never fires. So I hope you've got the logic of that. What is going on is something seems to be both taking path A and path B. Let me give it a name. I'm going to call it the quantum state, and I've given it a symbol as well. Big psi. It looks a bit like a devil's pitchfork. That might be the conclusion you'll leave with tonight, that the quantum theory is the very devil. Okay, so I've got psi path A. So this is a symbol that we use, but it also stands for quite a complex mathematical expression, which carries an awful lot of information about the kind of particle, about its energy, about its momentum, lots of properties. Psi of path B, the same, except there's going to be differences because it's path B. And what we say in quantum theory, Eleanor made this point, we talk about a superposition of these two states. Whatever these states are, whatever these psis represent, mathematically, we just add them together. Very straightforward. And it's the extraordinary feature of quantum theory that if psi path A is a solution and psi path B is a solution to the deterministic equations, because the equations are deterministic, then the sum of the two, the superposition, is also a solution. And you've met this before. You've all done, I'm sure, GCSE, O-level, A-level physics. We've all encountered waves that superpose and can cancel out or constructively reinforce each other, right? So mathematically, that's what's going on, and there's not a problem in understanding the mathematics. The entire question is, what is the physical interpretation when we have a quantum superposition like this? And what we've just seen is that it can't be understood as either or. In some sense, it's both. Okay, now, I've just talked about photons. We can do this with other kinds of particles, and we can look at different properties in the two arms, path A, path B. We can talk about energy A, energy B. We could talk about shape A and shape B. We can engineer this kind of experiment so we have a superposition and now we can do this with massive particles as well, which have different shapes. Most recently, they did it with buckyballs. Who knows what a buckyball is? 60 atoms of carbon, am I right? I think 60 atoms of carbon. Atomic weight of carbon? 12. Atomic weight of a buckyball? More than 720. So this is really quite a massive particle. It's got all kinds of structure. The quantum state, the shape A, describes that shape in exquisite detail. Now, Eleanor also talked about probabilities. Everything I've been saying so far is really about this psi, this quantum state, as if it's something really out there. Okay, so this is really why realism is what's driving this whole interpretative framework along. There really are buckyballs made of 60 atoms of carbon. They really do have the shape and the structure that quantum mechanics tells us that they have. And guess what? They really exist in superpositions of this form. Now look, we can carry on with this. We can push it more. And that's what a lot of people are doing in various laboratories around the world. One speculative experiment that may well be conducted in the near future is strands of DNA propagating down an apparatus like this. Okay. We don't expect to see any difference in the predictions of quantum mechanics. What happens, of course, is the experiment becomes much harder to do. If we can send atoms, if we can send buckyballs, if we can send strands of DNA, what happens if we send a person through this apparatus? And think about it like this. Every atom in your body will be subject to exactly the same quantum strangeness as the buckyball or the photon. So what happens to you? Now look, in a way this is a bit silly. Of course, you can't send somebody down an apparatus like this. You'd never get through the hole. What about the half-silvered mirror? You're going to smash your way through or something. Okay, so let's ask what really happens when you try to scale up an apparatus like this. Here's what happens. The left-hand side actually isn't significantly changed. There is no problem in the left-hand side producing people. I know that's going to sound a little bit strange, but you'll see why I say it in a moment. It's the right-hand side that gets completely lost. This is what we can't do. We can't demonstrate interference anymore. As soon as the mass becomes too large, too complex, no more interference effects are demonstrable. But this is realism. So what if we can't demonstrate the interference effects? The state is still a superposition. We just no longer can show the evidence for it. Okay, and now I say the left-hand side scales up. Really, the issue is just perform any indeterministic quantum experiment. And typically the output of a quantum experiment will be a superposition, as before. And now we're back to Schrödinger's cat. Because the point is, a big system, like a cat or a person, coupling to that experiment, we can do the maths, that big system gets to be into the superposition. It gets caught up in the superposition. And this is how it seems to follow from quantum theory. We must, if we follow the equations, we have superpositions of live cats and dead cats, and experimentalists seeing one outcome rather than another outcome. Okay. Now, in the face of this, because this sort of reasoning, we didn't have the beautiful experiments I just showed you, but physicists are very smart. They kind of saw the implications along the lines that I'm speaking a long time ago. It used to be a dilemma. Now I say it's a trilemma and it's a pitchfork, a quantum pitchfork. One option, abandon realism, change the philosophy. Now there's lots of ways of doing that. One way to do it, for example, is to deny that the quantum state represents anything at all in the world. It may seem to be about buckyballs and atoms, but actually no, it's about your beliefs. It's about your information. It's about your consciousness, about something else, not about the physical system. So that's one sort of approach. Guess who liked this kind of solution? The physicists. Okay, another one, change the physics. We know how to do that. To some extent, we can do that. We can do it with what we say non-relativistic, when we don't have, funny relativistic stuff going on, not particle physics, just slow-moving systems, of the sort that make up tables and chairs. Who do you think likes that proposal? The philosophers. And now I'm coming to Everett, we didn't have the third option, accept the implications and follow to the bitter end. Really follow through the reasoning. And this is what Everett did. So let's start off now with Cy. Cy's going to be the cat before anything's happened to it. I've got time going up. After a while, the experiment's been running, we get a superposition, the cat alive and dead. Fine. But now keep going. The superposition just evolves. We get another superposition, not very different from the first superposition. I've got A2 rather than A1, D2 rather than D1. There's some little differences. Keep going. Again, we get a superposition, the same superposition, but again, the two states involved are slightly different. Okay, so now first observation. Don't think of this as the cat in some weird state of superposition. Think of it as a live cat superposed with a dead cat. Not a cat in a weird state, a live cat superposed with a dead cat. And further look at this and see, we've actually got sequences, A1, A2, A3, that's a perfectly intelligible sequence of affairs for a live cat. A1 and A2, the cat will be walking around and meowing and maybe wanting to be stroked and so forth. I won't go on about what happens with poor D1, D2, D3 sequence. It's not a very nice experiment. Okay, so that's one very important aspect to this. There is a way of reading the state as unintelligible. What does it mean to be in two places, alive and dead at the same time? There is a way of reading it as intelligible as two distinct histories, and indeed a superposition of histories. Now, the further issue is probability, and this is the most fundamental in many ways, because after all of this is about, we've heard the word measurement problem, how do probabilities get into the physics? Because the equations are deterministic. How do probabilities arise? And this was Everett's amazing, really, suggestion, very simple, but remarkable. When you get the superposition developing from an initial state, that is the probabilistic event. And subsequent to A3, we get a further superposition, A4, B4. Each of those in turn develops into a superposition. What we've got, looking at these various histories, how many histories have I got now up there? I think 8, no more. 8 histories. Each of them has got a sequence of events that look actually in deterministic events. This is what Everett showed, that if you look at these sequences, what you find when you do repeated experiments, the same experiment again and again, you get frequencies, relative frequencies, just as if the world were indeterministic. Now, how to think about this? One way to think about it, the only way, I'm going to use the terminology worlds, the only way something chancy can happen in this world, if there's something chancy happening in another world, right next to us. And here's another way of putting it. How do I get you to write down 100 random numbers in a sequence? How can I tell you what that sequence is? It'll take me some time. But look, write down every sequence of 100 numbers. I just did it. I just get the whole spectrum. I just took a little sentence to do it in. It's a sort of the clue. The deterministic evolution is like enormous data compression. And it permits an expression of randomness, or what looks like randomness, as long as you've got all possible sequences. Okay, so this gives rise to a very typical representation of the Everett interpretation in terms of a tree-like structure. Reality is a tree-like structure. And this is actually a pine forest. So, oh, my word, I've completely forgotten that there's many worlds edited by... The fact that I'm getting 2.5% copyright royalties is completely irrelevant, and I didn't mean to put that up. Okay. Now we're back to, though, what is probability? We've got the structural characterization, it's branching, the development of a superposition. And when that gets to the macroscopic level, we get caught up in it. But what about the concrete numbers, the chances? And the answer is it's bound up with the, well, we could call it the weight or the size or the magnitude of these quantum states. Every quantum state comes with a magnitude, a number between 0 and 1. So however complex it is as a mathematical expression, it's got a simple number alongside it, between 0 and 1. So those quantities have got to be relevant to the relative frequencies, right? Because how else do we ever know how do we test a chance theory that predicts with some chance an event will happen? We've got to look at relative frequencies. We've got to do the experiment again and again and again. Okay, now if we do that, go back to this tree-like structure. So whatever it showed is that you can multiply up the weights of these states along the branches. And in fact, what you get is weights. I'm calling them weights, not probabilities. I don't want to prejudice the discussion. Let's just call them weights. You get weights for histories. And what you find, doing repeated experiments, is that the weights for those histories where the relative frequency is not what you'd think it from the ordinary standard common or garden quantum mechanics, right, where there's these rules that you apply only on measurement. The weights of those histories with relative frequencies in accordance with those rules is high. Those not in accordance is driven down, not to 0, but to infinitesimally small quantities. So, as it were, the main structure in the branching structure is of histories, all of whom have the statistics in accordance with quantum mechanics. That also Everett showed. Right. I want to come back to my quantum pitchfork. You see, I'm very fond of it. I think it's rather nice. I want you to leave you with although we'll be talking more further, with a way of understanding where we are in science. So I'm going to impale everybody on one of the forks of this pitchfork. I'm impaling Bohr, Niels Bohr, the Copenhagen interpretation. Here's what Einstein said: a tranquilizing philosophy on which the true believer can find a soft pillow on which to rest his head. Let him lie there. And this is the abandoning of realism route. Okay. Another route, change the physics. And now I'm impaling Steve Weinberg here. When he says this, I'm not as sure as I once was about the future. What he means by that is maybe we have to change quantum mechanics. And now I'm going to enlist an ally, another student of John Archibald Wheeler, Richard Feynman, but unlike poor Everett, his career was not destroyed. And here's what he says: if you think you understand quantum mechanics, you don't understand quantum mechanics. And what he meant by that is, it isn't easy. There is no simple answer. You can spend a lifetime in this subject and you will not have gotten to the core concept. Something is missing. Something is evading us. Something that we're not understanding. So far as I know, he never commented on Everett, and that's a shame. Science by letters. Newton's gravitational constant, big G. The velocity of light, little c. Planck's constant, h. I hope you've heard of all of them. Planck's constant, h? Who hasn't heard of Planck's constant, h? Oh, what a highly educated audience. I'm very impressed. I don't know that my first-year undergraduates are as good as this. So, in a way, it all began with Planck's constant. Now, what happened with big G, with gravity? I've got two people up here. One of them you'll recognize, it's Isaac Newton, but who's the other? Bruno, Giordano Bruno. Bruno should be a bit before Newton. Bruno was the one who thought all of the stars in the sky, they've got planets and they've got people on the planets. And that was absolutely intolerable. They had to burn him at the stake. I mean, just think about it. What have you got to do for redemption? There's an issue there. But look, the question that they were dealing with was, what is the visible universe? And of course, that question continues to this day. Newton could have, should have, got a grip on that topic within his own theory of gravity and didn't. It was only at the beginning of the last century that we really got to the view that the universe as a whole must be dynamical, must be changing in time. C. Einstein, velocity of light. Now the question that carries through from Einstein's work, what is time? And I don't mean here especially issues of time dilation, time going slow, time going fast. It's not so much those issues. It's what is time vis-a-vis all of the future events, all of the past events? Are they all just as real as the present? Think about that. How many trillions upon trillions upon trillions of events like this, and not with you guys all here and me here, but you take my point, macroscopic stuff. How many trillions of them have taken place just exist in the last 5 minutes? Half an hour? A million years? What is time? Well, I've got Schrödinger there and I've got Everett. And the question really that they initiated, and it's been in some ways the most baffling of all to philosophers, and this is partly why these ideas have become so intensely interesting over the last 20 years. The focus of attention has been enormous because there has been real breakthroughs with this question. What is physical probability? But the breakthroughs have entirely come through the Everett interpretation. The breakthrough is that this branching structure gives us an account of what physical probability is in a way that no other fantasy theory, let alone real scientific theory, has ever provided. The truth is, it's, as from a philosophical point of view, that question, what could objective probability possibly be, has become so difficult. The more you look at it, it's like Augustine with time. If nobody asks me what time is, I think I know, but as soon as somebody asks me, I haven't got a clue. So it is advances in that level, I think, that has partly led to this resurgence of interest in Everett's work. Okay, thank you.
Thanks very much, Simon. Okay, let's put some critical pressure on this now. Fay, I'd love to hear your take on this. What are your reasons for skepticism of this many worlds interpretation? What do you see as the main problems? What's your preferred way forward?
Thank you, Eleanor. Thank you, Simon. So, yes, as Jonathan has said, my assigned role this evening is to argue against the Everettian framework for understanding the nature of our quantum world. So first, what I'm going to do is mention what to my mind is a major difficulty for the Everett interpretation within its own framework. And then I will argue for an alternative framework to the Everettian one, in which there is one world and not many. So, as I see it, a major problem with the Everett interpretation on its own terms is the problem of probabilities. Actually, Simon has referred to that. I am not sure that he gave you an adequate explanation of how probabilities seem, or what appear to be probabilities, arise from a non-probabilistic theory. So we use probabilities when the future is uncertain. If there are two alternative outcomes, say, of a quantum experiment, then in the usual way of thinking about it, either one or the other of those outcomes will happen. We don't know which, and there is a probability for each one. But in Everettian quantum theory, the future is certain. In the Everett world picture, both outcomes definitely, certainly happen, each one in its own branch world. So work has to be done to explain how we can nevertheless make probabilistic predictions that we can use to test quantum mechanics. And to explain, we need to do work to explain how the theory is falsifiable in the usual manner. My own view is that the Everett interpretation is not falsifiable in the usual manner, and I am happy to discuss. I invite discussion on that point between Eleanor, Simon and myself in the discussion in a moment. To my mind, however, the strongest argument against the Everett approach is that it is based on the concept of the quantum state of the physical world, a state that evolves in time. Simon showed you how the superposition state of Schrödinger's cat will evolve as time passes. In the Everett interpretation, it is this state that corresponds to the physical world at any time. The Everett framework, therefore, does not do justice to the other revolution in 20th century physics, relativity. General relativity, or GR for short, revolutionized our understanding of the physical world. It taught us that there is no such thing fundamentally as three-dimensional space. The world, according to GR, does not consist of a three-dimensional reality evolving in time. Instead, GR teaches us to conceive of the world in terms of the concepts of events and histories. Now, an event is something that can happen in space and time. For example, rain in London tomorrow between noon and 1 p.m. That's an event. It can either happen or not happen. So it will either rain in London between those times tomorrow, or it won't rain in London between those times tomorrow. And a history is a particular detailed way in which an event can happen. So, for example, a history corresponding to this event of rain in London tomorrow could be that exactly 200,000 raindrops fall in exactly a particular pattern. And another history that corresponds to the same event of rain in London tomorrow could be that only 2,903 raindrops fall in another particular exact pattern of the raindrops actually falling. So there is a framework for quantum theory built on these same concepts, the same concepts that general relativity teaches us to conceive of the world using. These same concepts of event and history. And this framework is closely associated with one of the physicists that Simon showed you on the screen, Richard Feynman. So in 1985, Feynman gave a series of public lectures about quantum electrodynamics, the theory for which he won the Nobel Prize. And given the late date of 1985, it probably represents his mature thinking about the nature of quantum electrodynamics. And the lectures are contained in a book called QED, and I thoroughly recommend it. In the lectures, Feynman does not once refer to the concept of quantum state. He doesn't mention the word state once. He bases the physics on events and histories. When Feynman refers to a history, so the notion of event is exactly the same as the one I've introduced, for example, rain in London tomorrow between certain times. But when Feynman refers to a history, he means a completely detailed picture of exactly what all, not just the raindrops are doing, but exactly what every single elementary particle, electrons and photons and the other particles are doing. Now, Feynman teaches us that the probability of an event happening is calculated in the following way. You find all the histories, these detailed descriptions how the event can happen, and to each of those histories, the quantum theory assigns a number. And that number is called the amplitude of that history. It's just a word that you use to label the particular number that quantum theory assigns to that history. For in every event, you take all the histories that are the detailed descriptions of how the event can happen, you add up all of those numbers, You take each history, each one has an amplitude, a number attached to it, you add them all up, and then you square that. So you add up all these numbers and you square it, and that is the probability of that event. Now you may say, well, that's, what a funny thing that is. Who would have thought of designing a theory like that? You add up all these numbers and you square it. Why not cube it? Why not take it to the 4th power? Why square it? Okay, we do not know why those are the rules, but we know that it works. So when you calculate probabilities for events in this way, you get testable predictions about frequencies of repeated experiments that you can go out and verify. And for example, if we consider Eleanor and Simon's interferometer experiment, that's a very simple event. The event under consideration there is, does the photon arrive at the detector D2 and the detector clicks? There are 2 histories only in that experiment. One is the photon goes on path A, if you remember, and arrives at detector D2 and the detector clicks. And the other history is the photon goes through path B, goes along path B and arrives at detector D2 and the detector clicks. The 2 amplitudes for those 2 histories turn out to be equal and opposite. So when you add them, you get 0. So the probability for the event, which is the detector clicks, is 0. And that's why you never see that detector click. Now this framework of events and histories is often called Feynman's sum over histories. It's an alternative framework for quantum theory, alternative to the one that's built on the notion of quantum state evolving in time. It is predictive, it agrees with experimental results, and it is a one-world interpretation. There is one world in which every event either happens or it doesn't happen. So the event of Schrödinger's cat remains alive either happens or it doesn't happen. So the event that it rains in London tomorrow between noon and 11, it will either happen or it won't happen. The detector clicks or it doesn't click. So this sum over histories formulation, this alternative framework to the quantum state evolving in time framework, is not yet a fully developed interpretation. It's predictive and scientifically successful, but it is not yet able to say what the microscopic picture of the physical world is. The examples of events that I used to describe this framework were macroscopic ones, rain and detector clicks. They aren't events which pertain to detailed microscopic facts about the micro world pertaining to elementary particles. So the sum over histories interpretation is a work in progress. We're working on extending the interpretation to be able to give a picture of the microscopic world. But it is an alternative to the Everett framework. It's a one-world framework for quantum theory. And I'll end there, and I look forward to the discussion with Eleanor and Simon.
Thanks very much, Fay. Very clear explanation of a quite different one-world alternative to the many worlds theory that Simon was defending. Simon, you must want to come back to that.
Well, I do. I've got 2 things to say about this. The first is, of course, or maybe 3 things. Sorry. The first thing is, of course, we've got a predictive, extraordinarily successful one-world theory, which is just standard quantum mechanics. The issue is, can we understand it realistically? That's the question. So as long as we help ourselves to the notion of measurement, and, well, strange things happen when you do measurement, the equations are suspended, something else happens. If we are content with that, then be happy in a one-world setting. I don't like many worlds because I like them. I am persuaded of the intellectual case. So the crucial question then becomes, with respect to what Fay has said, is it realism? And in particular, does it dispense with these privileged moments when a measurement is performed? And the answer to that is that you've got them right there in the Feynman path integral, because you integrate from some initial data to some final data, and you get a probability. You've got to specify that initial and final data. What you can't do is say, just as time goes on, there are probabilistic events happening all the time. Each arbitrarily close in time to the one before, where you perform the same integral. If you did that, you would destroy interference effects. It's only because you don't do that that you retain equivalence with standard quantum mechanics, or indeed with Everettian quantum theory. So that's one point. But the other point that I want to say is that I love path integral formalism too, because you need it in doing calculations in particle physics. It's very elegant, it's very beautiful, it's been around for 50 years, everybody uses it. Within the path integral formalism, you can give an account of what the quantum state is. You can, as it were, reconstruct the quantum state. So, and especially at low energies, macroscopic things, you know, water, solids, ordinary materials, and so forth, everything at low energies, we can go back and forth between the path integral formalism and the quantum state language. So I don't really think it changes anything. So that's my response.
I mean, I think I'd probably sort of echo. I mean, there's a question about whether we want to get deep into path integral formalism, because of course we want to talk about parallel worlds. I mean, often what happens, one thing to say is a sort of dialectic move that happens often when you look at another interpretation, is that one thing that can happen is there's sort of either an anti-realism, or when you push on the realism side, it looks like these nasty being realist about superpositions crops back up. And there is a sort of endemic thing in quantum mechanics that if you can, and path integrals, you know, the superpositions are lurking there, right? Things go along all of these paths, and you put all the paths together, and each of those, one way of thinking of that is a sort of superposition of paths, right? So there's always this sort of lurking, and this is one of the things that makes the Everett idea really powerful, is there's often a kind of lurking accusation that if you take this thing seriously, if you take it realistically, you're back to taking the idea that the particle went along this path, and it went along this path, and it went along this path, and it went along that path. And once you're there, you're creeping close to the Everett interpretation. So I'm very curious, I think in the long term, to see how something like a path integral formulation teeters that line between lapsing to either instrumentalism, quantum mechanics is just about its predictions, or back into that thing where you start taking seemingly contradictory hypotheses seriously. And the moment you do that, you're creeping towards Everett, I think.
Thank you. Yeah, so I would disagree with Simon that this path integral framework for understanding quantum mechanics is standard quantum mechanics. So I'm not sure whether it seemed like you were claiming that it is just standard quantum mechanics and it's a one-world theory. But in standard quantum mechanics, a split is made between the quantum system and the measurement which takes place external to the quantum system. And the measurement is this strange, ill-defined interaction between a non-quantum measuring device, non-quantum observer, and the quantum system. But in this path integral way, or I should say, path integral is just another word for sum over histories. So this Feynman sum over histories framework, you do not make that split. You include everything in the quantum system. So the apparatus and the whole world is quantum mechanical. It's all described quantum mechanically. You do not make a split between classical measuring devices and quantum systems. So it's a cosmological theory. It does not require you to make a split. So it's not the standard way of understanding quantum mechanics. What I took from what Eleanor's point is that the sum over histories approach, the way I described it, it's as if, well, there's nothing strange going on at all. Where did all the weirdness go? Right? So the weirdness will come back if we ask of the formalism, what is going on at the microscopic level. They're the sorts of patterns of answers that we will get to questions like, did this event happen and did this event happen? Those will start to look very different from the ones that we would expect if the world was an ordinary classical world. So the weirdness will be hidden in the pattern of answers to questions about microscopic events. But it won't be a weirdness in the sense that there will be multiple universes or parallel universes, to get back to our theme.
I mean, should I just make a little... So I think that you're quite right that path integral formalism, you don't seem to need to introduce an observer, absolutely. But you can get rid of the observer within standard quantum mechanics as well. You can simply say, when you've got, and now the vagueness kicks in, when you've got a macroscopic state of affairs, then you calculate probabilities. And what the path integral formalism is saying, they don't typically apply it to macroscopic states of affairs, but when you've got an initial state or initial data, you've got final state, final data, you calculate the probability. In the traditional conventional formalism, that's like saying you're starting off with some, typically a macroscopic state of affairs. You could look at some latter macroscopic state of affairs, and you just ask what is the probability. And you can compute that using the quantum state, and it gives you the same answers as the path integral formalism. So really, what is the issue? From a realist point of view, the question becomes, what privileges the macroscopic state? How detailed can the macroscopic state be? How close together in time can these two macroscopic states be? Can we just allow it to, as it probabilistically evolve, like a random walk? But if we try to do that, we lose all of the quantum interference effects. That can't be what's going on. So it's very important within the path integral formalism that you don't, as it were, mess around with the intervening, all of those those amplitudes. You don't mess around with that. You let them, all possible amplitudes. And if you like, that's a little bit what Eleanor was getting at. It's like you've got a superposition of possibilities. So you mustn't mess around with that. And you've got to push that initial and final state far enough away from what you're interested in as a quantum theorist in particle physics. You're interested in some interaction, involving whatever, QCD, chromodynamics, electric weak. You're interested in the interaction, and the initial and final data is just scattering states. We've all seen photographs of particle data. You've got these particles spiraling out of this mess, this kind of chaotic thing. Those lines that come out, those are, as it were, almost like free particles. And that's what you compute in path integral formalism. Initial free particles, final free particles, in between some horrendous interaction, calculate the probabilities. And you mustn't regard a probabilistic process as taking place at each instant of time as you go through that intermediary stuff. Am I right, Fay? I think
Well, I wouldn't consider the pattern. You're thinking of the sum over histories as merely a calculational device for scattering experiments. So the world is not a big scattering experiment.
Right.
Things happen in between.
Right.
So it's a way to calculate probabilities of events for things happening in the middle.
Can I try and bring us back to sort of the big picture in some ways? I mean, Fay, you've written "take it seriously" on your piece of paper and underlined it several times. I think that was because Eleanor and also Simon, at various points you've mentioned the idea that the many worlds interpretation is the interpretation that takes quantum theory seriously. You often say it's realist. It's the realist one. It's taking it seriously. These other interpretations in some way can be accused of not taking it seriously, not being realist. I mean, Fay, I guess you disagree with this quite radically. Is it really true that this is the only way to take quantum theory seriously? Should we even want to be a realist if that's where it leads?
I think it just depends on what you mean by quantum theory. That's what I'm arguing with Simon about. So I think there are at least two different frameworks for quantum theory, in one of which this concept of quantum state is central, and it's about the quantum state. That's what the theory is about. So Simon wants to take that quantum state that the theory is about seriously, but my preferred way to think about quantum theory, or my preferred framework for quantum theory, there is no such thing as a physical quantum state. It's just not a concept in the theory, in quantum theory, and you can do without it, and you can use a sum over histories framework in which is empirically adequate for all the experiments we have done thus far. But there's just no concept of quantum state within it. So that's the disagreement we have. So
you're you think these guys are not taking it seriously in a sense, and that they're wedded to one particular way of formulating the theory, and there are better ways.
That certainly for Simon, I think Eleanor's probably.
I mean, if you want to, I was wondering about sort of bringing it back to sort of other thoughts about the many worlds interpretation, because I think there are a couple of things that also, I mean, so that you can have these different views about, and it is true that the way that Everett is normally formulated is very much puts the quantum state front and centre, and it's also generically true that the way you formulate the measurement problem and the way you describe quantum mechanics tends to push you towards certain solutions being natural, and there's going to be some of that going, it's a topic in and of itself, how on earth we try and frame this stuff in neutral grounds. I think that's part of the disagreement. But you can also take, I mean, there are lots of criticisms of Everett you can make taking it on its face.
Yes.
And one of them that's come up is where on earth are the probabilities? In a world where everything happens, what's the probability when it's at home? But Simon's addressed that a bit. But there's another little move, can I just push it? There's another little move that Simon made that I think was a bit more subtle in his presentation, and I thought I'd want to get him to comment on this, which is he went very quickly from the idea that, say, you have, a photon or something in a superposition state, and then, so you've got, listen to how I phrase that. You've got a photon in a superposition state, or an electron in a superposition state, and then it goes rather quickly to, you've got two cats, right? And there's actually a big metaphysical move that's going to be controversial, at least amongst philosophers, that gets made in the middle of this, and this is even taking many worlds theory on its own face. You've got to go from the idea that individual particles, we can think of an electron in one of these funny states, and then all of a sudden when we're talking about big things, we're talking about two cats. But those two cats are made up of fundamental particles, all in superposition states. So I just want to highlight how odd this is. We've moved away from a framework in which a cat is just made up of the fundamental particles that compose it. And somewhere along the story, cats stopped being made of particles. And I think that's probably something a lot of people will kind of push back on as a metaphysical creature.
Yeah. I mean, I absolutely thank you for that. And Fay, your focus on events is also helpful. Here's a way of thinking about it. Is a physical object, what is a physical object? And forget about quantum theory, let's just be classical. What is a physical object? Is it a series of events? Or is it something over and above a series of events? Is a physical object more like a process? Is it a very slow changing process? You look at a fast movie, fast framing of what's going on in the street, and it looks like a process is taking place. Is that the way we should think of streets and cars and buildings? Sequences of events, or something else, some further component, some further metaphysical notion? Philosophers have been debating this for a very long time, but I mean, almost with increasing urgency and desperation, if you like, because the options are not very good. I said time. What is time? It's a philosophical problem. It's a major field in philosophy, because the more you look at it, the more baffling it becomes. So I just want to make the general point. Thinking of a thing as a sequence of events is exactly the move that Eleanor was saying I sort of surreptitiously sort of slid in, and that's right. I did indeed surreptitiously slide over to that language of a history, like Fay actually, there are commonalities between us, and of a sequence of events. And an ordinary cat, not thankfully involved in one of these terrible experiments, we can think of as a sequence of events. But look, just on the point of the quantum state, take the buckyball and make it...
Let me press you there, Simon, on Eleanor's point. I mean, can't a photon also be then considered to be a sequence of events? So why is there, I think this is your question, Eleanor, why is there one photon, but two cats?
Right, good. So, indeed, the issue becomes, is the superposition, this quantum state which is a superposition, is that fruitfully modelled, analysed, its evolution through time, is that the thing that is informative when we do physics? Or, when you do have superposition and you've got lots and lots of particles in bound states and they're sort of stable, and those are in a superposition and you can't bring them back to interfere with one another, does that way of thinking of it as a sequence of states, each of them a superposition, is that informative? Or are we better thinking of a sequence of particle configurations, a sequence of particle configurations over here, in effect two systems rather than one system in a weird state? So that's the sort of way this conversation goes. But look, I do want to come back to the buckyball. It's very slow moving through the apparatus. Take a tenth of a second, and it's sort of within a micron or two. It's a buckyball. It's got geometry, it's got mass, it's got shape, it's got a lot of structure. What do you use to describe it with if you don't describe it by the quantum state?
It's a history. I mean, it will have a history, so it will be.
Yeah, I'm just looking at a fifth of just a tenth. It's very slow moving, just a tenth of a second. It's just in this bit of the apparatus. What is its structure? What is its shape? What is it as a thing? How are you going to describe it if you don't have the quantum state to describe it with? In a way, that's what the quantum state was invented for. So how do you do it?
A buckyball is an interesting challenge for this sum over histories based interpretation, because it's somehow not quite microscopic and not quite macroscopic. So I don't actually know if you were to interrogate the sum over histories interpretation and ask what would be the real description, the one world description of this buckyball. That's something I can't answer at our current stage of development of this interpretation.
Okay, thanks very much, all of you. At this point, I'd like to take a few questions from the audience. Now, we're quite short on time. What I'd like to do is take a batch of 3 and then throw those questions back to the panel. We have a roving mic. Please wait for the microphone to come to you before starting your question so that we catch it for the recording. Let's start here on the end of the front row, then we'll go back to the second row.
Hi, Isa Al-Hussayan. I'm a student at LSE. My question is to Professor Saunders. I'm going to press you on the sequence of events. We know that matter behaves differently in different stages of it. For like iron as a solid behaves differently as melted iron, and then atoms of iron behaves differently to both the previous stages. So the premise that you make when you want to justify parallel universes is that you move from the atom level. It's the same point that you've already discussed, but how do you justify the change of characteristic of the matter from the atomic world to the melted or the elements, and then to the solid? You're making that leap. How do you account?
Can we go straight to the next question?
My question is about the nature, the characteristics of the physical world that we take to be the means by which we infer its regularities and predictability, and quantum mechanics appears to confound at least 2 of those, causality and also the nature of a superposition. Is it possible that something which appears to actually contradict the laws of logic, the law of identity, law of non-contradiction, actually exists? And so I'm interested in some of the histories, whether you think that there's no real contradiction there, and I was interested to know from you, Simon, if you think that that contradiction actually does exist and is a challenge to the laws of logic. I understand that on Everett it wouldn't be, since you're simply diffracting into a different universe, so there doesn't seem like an actual contradiction there. But does the superposition in state itself confound basic laws of logic? Thank you.
Great. And Simon, you...
This is very important. One of the reasons why Everett's ideas, I think, are being taken seriously now in ways they weren't before is because all Everett gave was a very schematic analysis of repeated measurement. It was wholly schematic. There was no, in a way, real physics in it. It was just statistics. and amplitudes. What has happened since is that we've learned how to extract equations from quantum theory for large numbers of particles, in accordance with which these large number of particles behave as a fluid or behave as a gas, but with particles involving random walks through the gas, behaves as a solid. So we can extract from many particle quantum theory equations describing all of the forms of matter that we know. And guess what? We can't do it in classical physics. We just can't do it. Classical physics doesn't give us the resources to describe things like water or plastic or wood. Okay, and then the key point is the ways those equations are extracted from quantum mechanics exactly line up with the way that Everett got the statistics. Everett got the statistics, showed how you could get them. Subsequent people have shown how to get the Navier-Stokes equation, for example, or how to get the Langevin equation, for example, a form of matter which exhibits that. So that's partial answer to that. And on the point about logic, well, it was a move among philosophers and people in quantum theory to try to change logic, quantum logic, and is this going to give us a way of understanding everything? And mostly that just never really panned out. There's something rather important about the superposition principle. We've got this multiplicity, okay, there's masses, a multiplicity of masses. What's the total mass? Do we sum the masses? Have we gone from a state with one mass to lots and lots of masses? What about conservation of mass? What has happened? Okay, now the way that quantum theory is used to compute quantities like that, it's not like, one way of putting it is you use a kind of bit of quantum logic when you talk about superpositions. You say that what is a property of a superposition is what they all have in common. And otherwise you can't really talk about a property of the whole state. You can only talk about it insofar as all of the terms in the superposition have something in common. And that's a very interesting way. There's lots of things to play around with in that, and it's kind of fun. And it could even look a little bit like quantum logic, but I don't actually think there is any violation to logic.
Thanks. Thoughts from Fay?
Yeah, so I've hinted at, or claimed that we are working on an interpretation of quantum theory based on the sum over histories, in which we'll be able to give say things about the microscopic world. So, and based on the idea that every event either happens or doesn't happen. So, a microscopic event in the interferometer experiment that we have seen would be something like the photon goes along path A. That would be a microscopic event. And the photon goes along path B, that's another microscopic event. So it's looking like what is going to be the case in this interpretation is that the pattern of answers to the question of whether these events happen will not accord with classical logical rules of inference. So, for example, in that interferometer experiment, it could be the case that if we ask, does the detector fire? Let's say detector 1, the one that does fire. Does the detector fire? And the answer to that is yes. So it happens that the detector fires. So that event corresponds to the event, does the photon pass along path A or B? Right? So it's both of them. Does it pass along A and get to and make the detector fire? Or does it pass along B and make the detector fire? And the answer to that is yes. But if you interrogate the quantum world further and say, well, does it pass along A? You could get the answer no. So that event doesn't happen. And if you ask the question, does it pass along B? You would also get the answer no. And that event also doesn't happen. But so there you have a situation where A doesn't happen and B doesn't happen, but A or B does happen. And that's a violation of classical logical rules of inference. So it's looking like those kinds of violations of classical logical rules of inference at the microscopic level are going to be part of this sum over history's way of understanding the world.
Great. It'd be good to take one or two more questions if there are any. And then that will be all we have time for. It looks like there's one at the end of the third row from the back. And then we'll see how we're doing. Thanks.
Do philosophers and physicists collaborate directly on these problems, and how exactly does that relationship work? I'm wondering, do you play quite distinct roles, or are you both kind of playing both roles at the same time?
Yeah, good question.
Are we taking that directly?
Yeah.
Sure. So, I mean, I think it depends on the philosopher and depends on the physicist. There is a field called quantum foundations and a field called philosophy of physics. And there's an intersection between those two fields where what they do is virtually indistinguishable. There are also ends of those fields that would not happen in the other. And most physicists who are inclined towards the kind of philosophical end of quantum foundations are pretty interested in talking to philosophers. I mean, I think at the end of the day, I think the people who are right in this debate, notwithstanding what interpretation they believe in, have accepted that there's some sense in which we need two sets of skills here. I mean, solving paradoxes and picking out particular possibilities and working out how the possibility space works, that's something philosophers are good at, right? Not saying sort of woolly things, they're fairly good at. But of course, there are huge technical problems here as well. So I think that the best work happens at the intersection. It's also worth saying that the reason you do need a collaboration, I mean, one of the brilliant things that's happened in the last 100 years on this is that physicists have mostly stopped doing really, really bad philosophy. But it's extraordinary that some of the greatest minds of our time, the place they immediately went, as Simon pointed out, when they saw quantum mechanics, was a kind of ad hoc, rather mad anti-realism that put human consciousness kind of front and center. I mean, you can get quotes from absolutely brilliant physicists saying things that I would consider highly dubious for an undergraduate philosopher to say in a first-year essay. And so I think that one of the things that, there's still lots of disagreement, but one thing I think is enormously positive that's happened in recent years is there's some convergence of physicists and philosophers on the possibility space in the terms of debate. And just going, measurement has something to do with consciousness is sort of no longer something you'll hear thoughtful physicists say, for example. So I think it's not true that we always talk to each other, but there has at least been enough fruitful interaction to start getting this debate going in a much more positive way.
In Fay, you're our example of a thoughtful physicist today.
Oh, thank you.
How do you see it from the other side of the disciplinary divide? Do you need these guys?
Absolutely, yeah. I think challenges from philosophers have been extraordinarily helpful to my own thinking. I haven't directly collaborated on a project with philosophers, but certainly it's been very fruitful to me talking to them.
Could I just put in a
beyond the time when a single person could have all of these skills that we need. I mean, that Einstein was such a person, but today I think we need a community involving both sets of people.
Could I just say something about philosophy of physics? Because people may not know this. This is just straight sociology. Philosophy of physics didn't exist 50 years ago. When I started doing it, I was one of a really tiny number of people in the UK who was doing it. It's become a branch of philosophy, but it's really only in the last 30 or so years. So that's just a plug.
I mean, in closing, could I just ask kind of one last question, which is that if this many worlds interpretation is true, it's kind of big news, right? It's a complete radical, revolutionary overhaul in the way we see humanity's place in the world. If it's true, what do we do about that? How do we live our lives differently? Should it change anything about how we live our lives or not? I mean, Simon, you're the defender of this view. You think there really are parallel universes. Does it change how you live your life?
Well, let me say, it's not quite that I believe there are parallel universes.
I believe there are parallel cats.
No. What I believe is that the only way to interpret quantum mechanics realistically is in terms of parallel universes. There are parallel universes insofar as quantum mechanics is true, and I don't know if quantum mechanics is true. So, but on this issue of how does it... I think the impact is comparable to the impact that modern cosmology has or ought to have on every thinking person, which ought to be pretty colossal, actually. I think any thinking person contemplating the universe, just the classical one, forget about all of these others, ought to be overwhelmed, actually, with astonishment, amazement, or you name it. And these things are very potent. They're important. They're important to our creative, motivations, our intellectual lives, and so forth. I think what many worlds would do, and I don't see this happening in my lifetime, if quantum theory remains, cosmology hasn't gone away, Bruno was right about the stars and the planets and there's maybe life. We've still yet to see the evidence. It takes a long time for these things to really impact through. There are millions of people living in denial about Darwin. Okay, now what the Everettian perspective will do to our conception of reality, I think it will be transformative insofar as just exploring it is, well, it's sort of mind-bending, really.
Eleanor?
There's a funny contrast in Everett, because on the one hand, one of the Everettian strategies for showing that there are really probabilities is showing that all the ways we should make decisions are exactly the same in Everett, as if Everett wasn't true. So it's really important that Everett doesn't change the way you, say, bet on a quantum event, right? Or the way you would make decisions in your life. But there's this much more abstract thing, which is, what do you conceive of as a human being? What do you, you're now not seeing yourself. There are moral philosophers who've explored what you think about, thinking of human beings as sort of branching entities, what you should think of, how you should think of your morality, how you should think of personal identity, and thought that that's a really positive thing, that might make you less selfish, more altruistic. You have to work through those, but there are, and in the same way that perhaps, as Simon says, this cosmological vision, where we're a very small part of a very big universe, can sometimes have good effects, right? Appreciating that there's a much wider world beyond our ken can make us perhaps depressed, but perhaps better people. I think you can still have that reconceptualization of human beings as not the centre of the universe, and perhaps one human being as not the complete story of the centre of the universe, can have a sort of subtle effect on your conceptualization. But it's very important that it doesn't ultimately change what you do every day, because otherwise lots of Everettian problems fall down if you start making very different decisions.
No, but hang on a sec though, but this is very, very important. Let's take Darwin. Mm-hmm. Now somebody could say, look, it's very important that Darwin doesn't shake my faith in whatever, my religion. Because, heaven forbid, but heaven forbid, maybe you've just got to cope.
I just meant something different, which is that a crucial argument for Everett relies on the fact that we should make decisions in a similar kind of way. Right. So you've got to be a bit careful about self-undermining.
Absolutely. And what Eleanor is talking about, which may not be obvious to people, is the extraordinary role played by objective chance vis-a-vis rational choice. For some reason, which is never explained in any other theory but Everett, I'm sorry, it is explained in Everett, we conform our degrees of belief to the objective chance. We conform our degrees of belief. So my degree of belief that I'm going to, if I bet £5, I'll get, £10 or something, is going to be dictated by what I'm told is the objective chance. But why? And what is the objective chance that my subjective degrees of belief have got to conform to? So this is one of the many puzzles, it's not a paradox exactly, it's just unexplained. And the more philosophers have looked at it, the stranger it has become and the more difficult that problem has become.
That's a great note to end on, Simon. I'm afraid we've run out of time, but let's thank Fay, Eleanor and Simon for a fantastic discussion.